Welcome to Lecture 11. We are studying our coverages of oscillations and waves in this lecture. We start with the overview for Chapter 5, Oscillations and Waves. The chapter and the overview covers both oscillations, which this lecture set is focused on, and waves, which we will talk about more in the next lecture set. We do cover the terminologies for oscillations and waves in this lecture set, since there is so much overlap. For example, when we talk about period, frequency, amplitude, and resonance, these are all terms that are applicable both to oscillatory motion and wave phenomena. In the remaining lectures, the first section is on Intro to Oscillations, lecture that I am borrowing from Physics 4a. Most of the lecture is conceptual. We do get a bit more mathematical in the second half of the section, with some mention of sinusoidal trigonometric functions and derivatives. If you find those mentions useful, please give it a watch. You can also skip the second half. There's a large green text telling you when the coverage gets more mathematical. Then we talk about some features of simple harmonic oscillator motion, followed by a more extended discussion on harmonic oscillator motion of a mass on a spring and n-harmonic features of pendulum motion. Finally, we wrap up this lecture with an illustration of coupled oscillators, another demo borrowed from Physics 4a, which can be viewed as an example of resonance for the purpose of this lecture. We will use the next lecture set to illustrate wave and wave interference concepts, as well as going over some of the homework questions involving calculations, which aren't too many, thankfully. Now, we will start with the Chapter 5 overview. Hi, this is the overview video for Chapter 5, Oscillations and Waves. We start out with the oscillations to introduce some fundamental concepts and some terminologies as well. There are some sections that we won't be spending quite as much time on. The textbook sections are there for you to read on your own, and I'll point those out as I go over them in this overview. So we start out with oscillations. The way this mind map has broken it down, it's just the first branch here, but this covers sections 5.2, 5.3, and 5.4. So in section 5.2, we talk about periodic motion and introduce some basic terminologies, such as period and frequency and the relationship between them. These two are basically reciprocals of each other. If you have a period in unit of second, for example, that's the SI unit of period, time, then the frequency in the SI unit of frequency, hertz, is given as 1 over second. So 1 hertz is 1 over second, 1 cycle per second. And along the way, we also talk about what 1 cycle is. Some of this is pretty intuitive, but I think it's good to kind of double check your intuition in each new context. Then in section 5.3, we talk about simple harmonic motion or simple harmonic oscillators. I think I mentioned that you will see this again when we get to oscillations. Hooke's law setup, the typical setup is mass on a spring. You can also have a pendulum setup. And simple harmonic motion is what results from that Hooke's law restoring force setup, where the restoring force is proportional to the displacement. There are some new terms to introduce, like amplitude. And some of the features you will see will be what we refer to as a sinusoidal. It means when you graph it, it looks like what you'd get if you graph a sine or a cosine function that you might have seen in geometry or trigonometry, which is not part of the prerequisite for this class. I do have an Introduction to Oscillations video from Physics 4a, and most of it is conceptual, and that mostly conceptual description will end with a demonstration of showing that the position, velocity, and acceleration of a simple harmonic oscillator as a function of time looks like a sinusoidal wavy graphs. And section 5.4 covers forced oscillations, which we won't spend a lot of time on. Do take a look at the section and take away what you can. I think this natural frequency actually should have been along with a simple harmonic motion. In fact, that's the defining feature of a simple harmonic motion, which I will talk about more in other lecture videos. But to say briefly here, the defining feature of a simple harmonic oscillator is that it has a natural frequency of oscillation that does not depend on the amplitude. So even for larger amplitudes of motion, when you look at the frequency of the motion, it'll be the same frequency as a small amplitude oscillation. And that's what we refer to as a natural frequency. And I can see its importance in discussion of forced oscillations because something that we call resonance, that's what you see happen when you are driving something at a natural frequency of oscillation. And in a kind of forced oscillation system, if there wasn't any damping, then the amplitude would basically go to infinity because each cycle on resonance, you are putting more and more energy into the system. And if there's no damping to take away some of the mechanical energy, then it'll just build up without limit. But again, section 5.4, we don't really do much with it, but do please take a look at it. I do have some lecture demos that can be seen as example of resonance. I think in this lecture set, you will see the coupled oscillator demo. You can look at it as a kind of example of a type of motion that happens as one of the coupled oscillators drive the other oscillator at a resonant frequency. And you will also see the concept of resonance when we look at wave phenomena. Some of the wave phenomena can be described as a kind of resonance that's resulting from something driven at some sort of natural frequency. Okay, so that's oscillations. Sections 5.2 through 5.4. The rest of the chapter covers waves. The rest of the branches in these 5 out of 6 branches here. I don't know why mind map generated this way. The remaining wave sections are sections 5.5 through 5.9. And we don't really spend a lot of time on 5.9, so the number of sections are kind of even. But the waves are pretty important topic. So when I teach a Physics 4A class, I introduce the waves by saying, this is the one topic you will see in all 3 semesters of Physics 4A, 4B, and 4C. And even for us, you will see some of the wave concepts come back when we talk about light waves. And you will see these ideas get mentioned again when we do quantum mechanics. So it's pretty important. So wave fundamentals. There are some more terminologies to go over. So I will do a separate lecture video of oscillations and waves terminologies. I think that's probably the most useful thing for me to do. So you will see another lecture video of me going over the glossary terms from the section end with the help of Notebook LM infographic. So watch out for that. For the purpose of this overview, these are the terminologies that you will see introduced in section 5.5. Propagation, that's the kind of quote-unquote movement that waves do. What a wavelength is. I like analogizing this to period. Wavelength is like a period, but in spatial separation. Because one way of introducing waves is as oscillations in time and space. Whereas when we talked about oscillatory motion, that was just oscillation in time. When we look at waves, there is something oscillating over time, but you can also take a snapshot, freeze frame, and look at something that's oscillating over space. And wavelength describes that oscillation over space, distance between repeating identical parts. And wave velocity is the speed at which the wave propagation happens. I think for most people this is pretty intuitive, at least once you see it demonstrated. And finally, this is kind of the phrase that I have people memorize, that wave velocity or wave speed is the property of the medium. As long as your medium remains the same, as in if it's a sound, then it would be property of the air. If it's waves on a string, then it's property of the string, stretch the string. As long as the medium stays the same, the wave velocity will stay the same. It's kind of comparable to how there was a natural frequency of oscillation for simple harmonic oscillators. The frequency of oscillation didn't depend on the amplitude of oscillation, and in a similar way, the wave velocity doesn't depend on the amplitude of the wave disturbance. It depends on the property of the medium. So you can change the wave velocity by changing some relevant property of the medium. And section 5.5 also covers wave types. Sometimes I forget to lecture on this because this is sort of kind of wave terminology that you could skip and still cover the rest of important topics like wave interference. But I do think it's important to cover just so that you know what they are. So we categorize waves as transverse waves and longitudinal waves. And many types of waves are one or the other, not both, although nothing prevents them from being both. Some of the most often used examples of waves are transverse waves. I do like illustrating transverse waves better. So light is an example of transverse wave, and waves on a string, like on a guitar string, or there's a simulation I like using, those are transverse waves. And I guess if you know the Latin root of transverse, then it's sort of what it sounds like. The disturbance in the wave is perpendicular to the propagation direction. And longitudinal waves are where the disturbance is in the other direction. The disturbance is parallel to propagation. So sound waves in air is one good example. And P waves, this is a component of earthquake wave. I think P stands for pressure. And earthquake actually contains both transverse and longitudinal waves. The transverse component of earthquake wave is called the S wave. S stands for shear. And the waves do have different property. I think one wave travels faster than the other. I forget, I'm not a geologist, but I think P waves travel faster. And then the shear waves comes after. But, if it's important to you which is faster, look it up. Don't quote me on that. I'm not a geologist. I'm just trying to remember something I read a long time ago. So those are the two types of waves. Depending on whether the disturbance is parallel to propagation, which is a little bit harder to illustrate, or if it's perpendicular to propagation, which is a lot easier to draw, like for waves on a string. So that's it for section 5.5. Section 5.6 covers what I'm most excited about and what you will see some demonstrations of. It's the wave interference. And wave interference is fascinating because it results from property. It's in some sense very simple. We introduced something called the superposition principle. And I say we give it such a grandiose name because it's a really simple principle. It says that when you have two waves that are overlapping, you simply add them. You don't do anything complicated. You don't take average. You don't multiply. You simply add them. It's the simplest mathematical operation you can think of. And because it's so simple, we give it a grandiose name, superposition principle. But it does result in pretty interesting features that you will see through what we call constructive and destructive interference. Constructive interference happens when waves add in phase. That means whenever disturbance from one wave source goes one way, disturbance from the other source is going the same way, so their impact is added together. And destructive interference happens when they are out of phase, meaning when the disturbance from one source goes one way, let's say up, the disturbance from the other source goes the other way, let's say down, and they kind of cancel each other out in the process of adding in the superposition. And to work out this can be pretty mathematical, so we will skip that part, but we will look at the phenomena, some of the interesting features that result from that. One is standing waves. I think I have a simulation demo using standing the waves on a string forming a standing wave there. That's where you can see a visual illustration of nodes. That's the standing part of the standing wave, where there's no disturbance. Kind of point just stays in place even though nothing is physically holding it oftentimes. Antinodes are the opposite of nodes. It's where you have maximum, most possible displacement. That's basically where you would measure the amplitude of the standing wave. And the fundamental frequency would be the lowest frequency at which the standing waves occur. And depending on how the standing waves is set up, the higher frequencies could occur as some integer multiple of the fundamental frequency, but it's not going to be always that. Look for some examples that I have. I have a standing waves demo using simulation, and I plan to record some videos using what's called a Chladni plate that shows the standing waves in a two-dimensional space. And there, the higher harmonics definitely won't be an integer multiple of fundamental frequency. It's a little bit more complicated, but watch out for that demo. Beat also occurs from wave interference phenomena. It says similar but different frequencies. So I guess one way you could see this standing waves, the kind of illustration of it happens in space. It's all spatially separated. You can look at where the nodes are, where the antinodes are. Beat is something that happens in time, and it results from a superposition of two waves of a slightly different frequencies that results in what looks like basically an amplitude modulated signal. You will hear an illustration of beat in one of the lecture videos. So that's section 5.6, wave interference. In sections 5.7 and 5.8, we'll look at sound as an example of a wave, and one example that a lot of people are familiar with, hear about or hear directly, and it's the basis of music too. These interference phenomena, standing waves of sound, is basically how most of the musical instruments work. So when we look at sound, we are talking about vibrations, but it's vibrations in a specific range, what we call audible range of 20 hertz to 20 kilohertz. And this is a pretty wide range. So the frequencies that you personally will be able to hear will be definitely narrower than that. I myself can't quite hear anything lower than 30 hertz. So even though 20 hertz is the textbook boundary for infrasound, but for most people, you will stop being able to hear it before it gets to 20 hertz, but with a large enough amplitude. Think of a big bass speaker. You might be able to kind of feel it around this. And ultrasound, I'm old, so I have trouble hearing frequencies above 10, maybe 12 kilohertz. But I think even for very young people, unless you're a baby, even for like college freshman students, above 15 kilohertz, I don't think I've seen a lot of people who can hear above 15 kilohertz. So it'll be a very rare person, even among youngsters, who can hear at 20 kilohertz. And in the context of music especially, we sometimes talk about pitch. It's basically, frequency, but, your perception of frequency. I'll leave that there. And speed of sound. So speed of sound is one of the good kind of practical numbers to have memorized. So speed of sound under the usual circumstances like room temperature, atmospheric pressure, air, dry air, is about 340 meters per second. So in a thunderstorm, you can actually use this to estimate how far away lightning strikes were by observing a lightning light and counting of seconds until you hear the thunder. Then from that, by knowing the speed of sound or assuming it, you can estimate how far away the lightning strike was. I think you have some homework questions that's based on that. It is affected by temperature, and I forget if it's affected by pressure. It might not be. I used to think it did, but I read somewhere with the change of pressure, basically at a constant temperature, the change in density just cancels out whatever the effect would have been. The rigidity, I think that's more about speed of sound in a solid matter. So speed of sound in a solid matter is generally faster than speed of sound in air, and it'll depend on the material property. So that covers through section 5.8. And there's this branch that this mind map is calling advanced phenomena. And Doppler effect and sonic boom. Oh yeah, I think these are all section 5.9 topics. I used to have essay questions based on these. I might do some ungraded discussion based on this. I'll see. For the time being, do take a look at section 5.9, but there aren't that many homework questions that you will need this content to answer. But these are all fascinating, like sonic boom. That's why there are limitations on supersonic flights over land. And this is all fun stuff. Cherenkov radiation that relates to nuclear physics and particle physics. It's all fun topic, but we have limited time this week, and if possible, I'll try to do something that relates to this, but I don't have any lectures on this. So that covers chapter 5, oscillations and waves. Again, this is a fun topic that covers a lot of areas of physics. So I hope you find it interesting and recognize the applications of these concepts in future topics that we'll cover. Thank you. Bye. So in chapter 5, oscillations and waves, we introduced quite a few terminologies. So I thought it would be good to record this separate video going over all the waves and oscillations terms. I think a lot of this should come pretty intuitively because some of them we are just using everyday terms. But as with anything technical, I think it's good to be precise and clear. So I'll start from the top of this infographic generated by NotebookLM. Some of the terms that occur earlier, it's moved to the end under systems and sound. When those come up, I'll just briefly mention it and just cover them at the end. I can kind of see the logic in the organization. I'll just mention it as we go. And I saw a bunch of typos as I was looking through it. I'll correct those as we go. So key concepts in oscillations and waves. A glossary of essential terms for oscillatory motion and wave phenomena covered in chapter 5. So some of these core concepts are hopefully something that you are already familiar with, what you would have kind of assumed from your knowledge of English language. Like oscillate, it means to move back and forth regularly between 2 points. So in everyday term, this regularly might not be part of it, but the kind of the oscillation phenomena that we'll look at will only be ones with a regular feature to it. So when we look at a periodic motion or period of a periodic motion, you will be able to see a motion that repeats itself. Wave, I have an introduction to wave video where I'll go through it a little bit more, but I think this is a good succinct description of it. A disturbance that moves from its source and carries energy. And quite pointedly, not necessarily and almost always not matter, at least over a long distance. You'll see more about waves in the next lecture. So any ambiguities here hopefully will be resolved by that lecture. Simple harmonic motion, this is really the big topic we are covering in this lecture set. Simple harmonic motion or simple harmonic oscillator, it describes an oscillatory motion where the main thing that's driving that oscillatory motion is the restoring force described by Hooke's law. As a reminder, Hooke's law said that the spring force, that's really what it describes, is given by minus kx, where x is the displacement, which is a vector, and force is a vector, and that gives meaning to this minus sign. The force in Hooke's law is opposed to the direction of the displacement. That's why it's a restoring force. And the important feature is that this is a linear force. it's proportional to the displacement. It's not proportional to the square of the displacement or cube of the displacement. This mathematical feature results in a characteristic that defines a simple harmonic oscillator. And in fact, I think that's the first of the terms that you will see later. The defining feature is called natural frequency. Every simple harmonic oscillator has a natural frequency of oscillation. For like a mass on a spring, the natural frequency of oscillation in radians per second is the square root of spring constant divided by mass. And what's important here is that it doesn't depend on the amplitude that we are going to talk about soon. Now, the next few terms that you will see, they apply both to oscillatory phenomena and wave phenomena. And I think this is really one of the main reasons to do oscillation first, because we get to introduce these terms in the context of oscillation where it's a little bit simpler. So you have frequency, that wow, there are so many typos. It's the number of events, not accents, or oscillations per unit of time measured in, that's weird. Hertz, the abbreviation is correct, and it's spelled Hertz. It's a guy's name. He's someone who demonstrated the light waves experimentally for the first time. Or I guess he demonstrated that electromagnetic waves travel at speed of light. That's what he demonstrated experimentally. And period, I think in the chapter overview video, I mentioned the period is reciprocal of a frequency. It's the time it takes for one complete oscillation to be completed. So if you give a letter T to period, let's say in seconds, and give letter F to frequency, then there's a mathematical relationship between them. So period would be measured in seconds, then frequency is given by 1 over period. Or you can reverse the relationship and say period is given by 1 over frequency. So these terms apply to oscillations, and there's one more term that you will see in the context of oscillation, that's the amplitude. And what is exactly meant by amplitude? It can change quite a bit depending on the setup. But I think what it has here is a good default definition. It's the maximum displacement, where the displacement might not necessarily be the spatial displacement, it might be something else, but maximum change from the equilibrium position or condition of something that's oscillating. Not oscillating. Let me just spell here oscillating. So for the literal description of this, it applies to mass on a spring, for example. If you have a pendulum oscillation, then what you call displacement would be an angular displacement from the equilibrium position. And there can be other more mathematical oscillations and waves where the displacement might be some other property that's not measured in meters. So those terms are introduced in the context of oscillations, and they mean pretty much the same thing when we talk about waves. And in the context of waves, we introduce new terms. One of them is wavelength. It sounds like length of a wave, and in some sense it is. It's the distance between adjacent, I think A and E are swapped, adjacent, identical parts of a wave or repeating parts of a wave. So this picture here illustrates that. So the picture that's drawn here, you can think of it like a snapshot in time of a wave. So this represents a peak-to-peak method of measuring wavelength. So you start at peak, go through a trough, and then come back to a peak. That'll be a wavelength. You can also measure it trough to trough. So if this is a snapshot of a wave, then going from trough to trough, that will be a wavelength, lambda. That's the usual letter we use. You can also go to equilibrium, but you have to be careful. You have to remember to get to the same kind of condition at the equilibrium. So here it's not quite the same, because before it was moving down, here it's moving up. So you have to skip that and come here for the correct measurement of wavelength. And as I'm drawing these pictures, if what I'm labeling as wavelength kind of looks like period, that kind of similarity, it's to be expected, because a period and wavelength are analogous to each other. Because period and wavelength are analogous to each other. Period is how much time it takes for the pattern you see either in oscillations or wave motion to repeat in time. And wavelength is the spatial distance it'll take for the, it would now only happen with the waves. That's how much spatial separation it takes for the repeating portion to repeat. So whether this represents a period or wavelength, it kind of depends on what this is illustrating. If this is, so what I'm labeling here would apply if you took a snapshot at t equals 0, and what you are plotting here is as a function of position, some sort of displacement here, then this would be illustrating waves and not period, because period is in time. But you can also imagine taking measurements of a single position. Instead of freezing it to t equals 0, you can imagine freezing the where you sample your motion at x equals 0 at a particular position, and you track the motion of whatever is going on there as a function of time. Then it wouldn't be wavelength here, it would instead be the period here. So you kind of have to know what an illustration is plotting before you can say for sure, is it representing period or wavelength? So let me erase all these annotations. So that's wavelength. And wave velocity, I don't know what that subscript there is. It would make sense as like a W, V sub W would make sense. It's the speed at which the disturbance, the wave, moves through a medium. So in a wave motion, there might be some other kind of speeds and velocities, like how quickly, for example, a piece of string is moving within a wave on a string motion. But wave velocity is different. The motion of, quote-unquote motion of the disturbance, which is the wave motion, how fast that's moving. I think it's actually quite intuitive for most people once you see it illustrated, like for example in a simulation. And this wave velocity is quite simply related to two of the quantities here, the wavelength, and I usually relate it to frequency. And this is the expression that I have memorized. I recommend that you memorize it. The wave speed is equal to frequency times the wavelength. And when you work out the units, you need to work out, because the velocity should be in unit of meters per second. Wavelength, being a length, should be in unit of meters. And frequency, being reciprocal of period, time, it should be in 1/seconds. And this expression might make it look like wave velocity depends on frequency and wavelength, but it doesn't actually depend on frequency and wavelength. It's a property of the medium. And so if you don't change the medium, but simply change the frequency or wavelength, that'll mean actually one of these other two quantities have to change, so that the wave speed, the property of medium, remains constant if nothing about the medium changes. So those are core key wave terms that you need to know to specify important characteristics of wave. And the next section covers types of waves. This is, I sometimes skip because it's kind of, this, let me box it here. This, it kind of stands on its own. So it is, I think, something that you should know, idea of transverse wave and longitudinal wave. It's important to know, but suppose you skipped it, we can talk about the rest of the wave concepts and interference without really being explicit about, are we talking about transverse wave or longitudinal wave? And these graphics illustrate transverse and longitudinal pretty well. So in both of these pictures, wave propagation direction is, let's say, to the right. Then whether the wave is longitudinal or transverse, it depends on in what direction is the disturbance. in this wave on a string, the disturbance is in these directions that are perpendicular to the propagation direction. That's what makes it transverse. It's a wave in which the disturbance is perpendicular to the direction of propagation. In a longitudinal wave, imagine a slinky that you kind of push and pull to create these regions of, I guess, in a sound wave, you might call this rarefaction. And I think, is this called compression? This might be called compression. Let me move this out of the way. Rarefaction and compression. And as it's doing that, each of these rings of the slinky, it's moving in this direction. And this is either parallel or anti-parallel to the propagation direction. So it's a longitudinal wave, a wave in which the disturbance is parallel or anti-parallel, 180 degrees, to the direction of propagation. Again, good terms to know. There are some additional examples of transverse and longitudinal wave in the textbook that you should take a look at. And really the fun, interesting, fascinating part of wave phenomena is what this infographic is calling wave interaction, or I guess I prefer the term wave interference. And I think the irony of both of those terms is in the context where superposition principle applies, really the key thing is that the waves are not interacting. They're not interfering in the sense of impeding each other's movement. So superposition principle, it's a consequence of what's called linear medium. It's a linear property of waves, and it actually happens in many other physical phenomena. So when two or more waves arrive at the same point, according to superposition principle, those two disturbances, they simply add. And the impact of the disturbances simply add. No complicated mathematical operation, and that simple mathematical operation is a result of the two waves, frankly, not interacting with each other. The one wave moves as though the other wave wasn't there. Now, that doesn't mean there aren't interesting features that you get to see. You will get to see these features most clearly in the example of standing waves. So in standing waves, you have places called nodes where destructive interference occurs. That's where the way the waves are set up, these two counter-propagating, one traveling to the right, one traveling to the left, they kind of happen to cancel each other out at all times at these locations. That's where you get destructive interference, you get nodes. And the places where you get constructive interference are what we call antinode. It's these spots here. That's where you get the most disturbance. This is what we call antinode. You get constructive interference. Let me correct some typos. So constructive interference when two waves superimpose in phase, creating a resultant wave, not resultant, with a larger amplitude, not simplitude. Destructive interference when two waves superimpose out of phase, creating a resultant wave with a smaller or zero amplitude. And most examples we'll look at, we are just looking at zero amplitude. We don't really look at partial destructive interference. And of course, they are all in between points. But we're sticking to conceptual points here. So standing waves, that's where you will see this example of wave interference. You also have beat phenomena. And I want to show you additional lecture demos involving additional wave interference in two-dimensional space. I need to record the video with a Chladni plate, and I do have a video of water waves that I will put it into the next lecture set along with other examples of wave interference. So standing wave, that's a wave pattern that appears to vibrate in place. I like to say the standing part of the standing wave are the nodes. But it's really the entire thing. Every point in the standing wave, you can kind of look at it as something that's oscillating up and down without sideways motion. It kind of comes from addition of these counter-propagating waves. So formed by interference of two identical, meaning same amplitude, waves moving in opposite directions. I think amplitude is the only way they can be. Same frequency also, that matters. So same amplitude, same frequency of waves that are moving in opposite directions. All right, so I think we have some additional terms referring to sound and I guess the systems. Some of these terms really should have occurred above, but for whatever reason, this infographic was generated with these at the end. So resonance and natural frequency is something that you see in the context of oscillation. Although, resonance it occurs so often, and in the context involving waves, I can see kind of grouping it with the wave phenomena. You can look at beat as a kind of resonance. Standing waves are definitely an example of resonance. And I think this is a concept that's equally applicable to just pure oscillatory or wave phenomena. Natural frequency, this is really referring to simple harmonic oscillator or simple harmonic motion. Sometimes I think you can talk about natural frequency of like wave on a string for standing wave. That's somewhat related to fundamental frequency. So in some senses, these can sound similar, but they are a bit distinct. I guess I could say they are related. At least in the context of resonance, natural frequency and fundamental frequency are quite similar. In a way, they relate to resonance. So how they relate to resonance are similar. So natural frequency, there are typos again. The frequency at which a system oscillates. Let me just rewrite. This is oscillate when not affected by a driving or damping force. Driving force definitely, because in a driven system, the eventual frequency of motion will simply match the driving force. And damping force, I guess technically, when a simple harmonic oscillator is damped, the damping will actually shift the oscillation frequency a little bit. So yeah, I think when not affected by a driving or damping force, makes sense. It's also the frequency in which, if you are driving a damped oscillator, you will see the resonance occur, because that's the frequency where if you're driving at the right frequency, you will build up energy in the system over time. And damping force, it's usually a like frictional force that converts the mechanical energy of an oscillation into thermal energy, or other forms of energy that's not mechanical energy, or maybe just simply takes it out of the oscillating system. And I mentioned the beat as one of the wave interference phenomenon. You have a demo video of a beat phenomena. Please take a listen. It's fluctuations in amplitude or amplitude modulation that's produced by superposition or interference of two waves of similar but not identical, so different, similar but different frequencies. The difference in the frequencies becomes the beat frequency. So this separation is related to beat frequency. And audible range, I think I talked about it in the overview video. It's the range of sound frequencies that people can hear. And this 20 to 20 kilohertz is really the inclusive range, in the sense that most people, even the oldest people, I don't think can hear down to 20 hertz, maybe 30 hertz. So for most people, your range that you can hear will be something smaller range. I personally can probably hear down to maybe 30 hertz and up to maybe 10, 11, 12 kilohertz, and higher than that I'm too old to hear. But even the younger students, I don't think I've seen most people hear above 15 kilohertz. So those are all the important terms. There are some additional terms in section 5.9. But I think this infographic is actually right to leave those out, because you don't have any homework problems out of section 5.9. I do encourage you to give it a read, but it's the topic that I have to kind of If not skip, at least not spend a lot of time in. So I do encourage you to read section 5.9, but the terminologies in section 5.9 are not covered here for a good reason. So this is it. Let me know of any questions. Thank you. So with the oscillations, this is something you have seen before. You have seen me use this mass on a spring as a demo for a bunch of different things many times now, right? This is not anything new, right? So what we are now going to do today is we are going to spend a little bit more time looking at this in detail. We are going to, so you have seen this setup, and we have used this setup to talk about spring force, right? Where you see this mass come to rest. That's the equilibrium position. You can draw the free body diagram. Gravity pulling it down, spring force pulls it up, it balances here, right? We have also used this setup to look at conservation of energy. So you know how to answer questions like, if I pull it down by some amount and let go, and somehow I tell you the spring constant, then you can answer the question of how fast is it moving when it comes back to the equilibrium position. So from what we have done so far, you can answer questions like that. So if I tell you, okay, I displace it by, 20 centimeters, and I tell you the spring constant, and I ask you, when I let go, how fast is the mass moving when it reaches the equilibrium position? You can imagine answering that question? Yes? Yeah. So this is a setup that we have seen. But what we haven't done is really go into a deep dive and really look at it in detail. So you will maybe notice we have never done this. We have never tried to describe the position of this mass as a function of time. When it's at the equilibrium position, its acceleration is 0. So right now you can see that its acceleration is 0. But even when I pull it down and let go, we'll look at it in a bit. When it's at this position, its acceleration is actually still 0. But when I pull it down and let go, then at this position, its acceleration is clearly not 0. It's upward. And when it reaches up here, its acceleration is downward. So as this oscillates up and down, it involves a changing acceleration. So this doesn't quite work well with any of the tools that we have developed so far. That's why we haven't tried to do this description yet. We have sort of nibbled at the edges of it. We try to describe what we can by using conservation of energy. But the problem with the conservation of energy is that it doesn't relate directly to time. So what I'm telling you now is that at this point in the semester, I think we are ready to handle this in the full scale. We are going to go into the actual mathematics and actually derive the position as a function of time. But before we go into all of that, because it's going to get calculus heavy. So this and next week is going to be another calculus heavy portion of the semester. But I don't know, in case you are recalling back to how difficult kinematics were, in my opinion, this is actually easier. Because kinematics is it's the kind of thing where you thought you understood it when you took calculus, and then you come to this class and you realize that you didn't understand. Those are the toughest things to handle. But here, because it looks complicated, you didn't think you knew it, but turns out a lot of the stuff we are going to go over today and Thursday are things that you actually know. It's nothing that's radically new. So, but let's just start out with some intuitive answers. That's what problem 1 in your worksheet 13 is about. I have this exact demo set up before I had to leave for the meeting. And we are going to go through this. So this is one question that we actually go through in class. We'll go through this so that first we'll guess at some answer that you can guess intuitively. And then we'll do the experiment. Let's see. I have this thing set up to actually make all the measurements. We'll do the experiment to see how it goes, and then we'll do that. So let me do this. Let's see. I guess for part A, I'm supposed to demonstrate to you what this setup does. So you've seen this motion detector setup before, right? And I set this all up so that when I start to collect, then it'll read the position of the mass at 0. I zeroed it so that this motion detector thinks this is the 0 position. If it goes closer, it'll be negative. It goes farther away, it'll be positive. Good? Nothing here seems surprising. That's how you would expect it to work. So let me make up some space for this. So it's asking bunch of questions. When it is in this position at rest, let me call this I. And then later on, it's going to ask when the mass is above the equilibrium position, call this 2. And when the mass is below the equilibrium position, call this 3. Good? And hopefully, this is reminding you of what we were doing before we went to conservation of energy and momentum. So let me draw a free body diagram. Let's draw a free body diagram for each of these 3 cases as we go through and answer the questions that they are asking. So when the mass is here at the equilibrium position, what are the forces acting on this mass? Gravity and spring force. So let me just kind of draw a diagram for that. mg. And the spring force, do you remember the formula for spring force? Yeah, so the minus kx, or the magnitude is k times x. That's Hooke's law, right? So let me just write down that k times delta x for now. This is coming from Hooke's law that hopefully you remember. Okay, what's the net force? It's essentially the same question. How do these 2 forces compare? One way of asking it. Or the second way of asking it, what is the direction of net force in this case? Net force is 0. How do you know it's 0?
They're equal to each other. It's not moving, it's at rest.
Okay, so let me ask the other version. How do you know that these 2 forces are equal to each other in magnitude? You cannot say because net force is 0. Because that makes it circular. Maggie, you said the acceleration is equal to 0?
Right.
Yeah. So, Stephen, is that what you're going to say? Yeah. So, because you know Newton's second law. Net force is equal to mass times acceleration. So, I mean, you can see that acceleration is 0. It's at rest. It's remaining at rest. So, acceleration is 0. So, the net force is 0. That's most of it already have that intuitive feel that here these 2 forces are equal. And the reason it's equal is because net force is equal to 0. All right, let's go through 2 and 3, which is less trivial. So 2 says if the mass is above this equilibrium position, is there still gravitational and spring force on this mass? All right, yeah. And when I let go of my hand, both hands, what is the direction of net force? Downward, and you know that because it accelerates downward. And so what does that tell you about the relative magnitude of the force? Yeah, spring force is smaller. So that's because, as Stephen said, it's because spring force decreased. Gravity is still mg, it didn't change. But if I lift the mass a little bit, then this k times delta x, it's smaller, because this delta x is smaller, right? So here right now I'm trying to do the pure spring force plus gravitational force description. So this is the actual equilibrium length of the spring. As you pull on it, there's an increasing amount of force pulling it back up. So equilibrium position is where the spring force and gravitational force balanced. When I push it up, spring force decreases and the net force points downward. And you see that in the motion. What about when I pull this down? Someone other than Stephen, maybe. Arjun? So once again, 2 different versions of the same question. Is how does the gravitational force compare to spring force? One version. Or the second version, what is the direction of net force?
Downward, right? So if you move your hand, then it will be upward.
Yeah, so I'm asking about when I remove my hand, so you know it's going to go upward. So what does that tell you about the direction of net force? Upward, right? I'm asking always about what happens when I remove my hand, not while I'm holding it. Yeah, so there's a net force upward. And how can you explain that in terms of these two forces that we identified? Does gravitational force change? No, that's still mg. So why is the net force upward now? Spring force increased, right? Because I stretched it out more. Yeah, so you feel like we have intuitive feel for this? This is not too complicated? Okay. So the next part is the part where I want you to ask you to spend a little bit of time predicting. So I'm going to do what this problem describes. I'm going to lift the hanging mass up, lift it to somewhere, okay, I can't lift it any higher than this, up to about this point. Let me actually mark that height so that I can do it consistently. So I'm going to lift this mass to about this position. All right. And I'm going to let go. And you can actually look at it. So you have seen this many dozens of times. What happens now is not anything surprising. But what I'm asking you to do now is I'm asking you to actually sketch the position. So this is a function of time. But for convenience, each different times are described with a qualitative description. There's so let me try to let me number this 0, 1, 2, 3, 4, and let me try to just say it out loud as it goes through those different times. So this is 0, 1, 2, 3, 4. Okay, it's way too fast. But you get what I'm trying to say, right? 0 as it goes down. 1, 2, 3, 4. Good. Did I label 4? Yes. So it's the times are in sequence of 0, 1, 2, 3, 4. Good. So you have some sense of intuition about what that should look like. So I want you to take a minute, sketch it, what it should look like. I mean, it's something that oscillates up and down, but there are many different ways something can oscillate up and down. So I just want you to sketch it out of your intuitive feel, and you'll compare it with the actual experimental result when we do the experiment. All right, I think some people have a more reasonable picture than others. I guess it's easier to actually do it and see. So let me do the experiment. Because, let me wait. I did not think this through. Are these writings annoying, or can you look at the graphs through these writings? Okay. So let me do it this way. I'm going to lift it. So I'll hit collect. And I'm going to wait like half a second or maybe about 1 second. So there'll be 1 second of flat line. So hit collect. Okay. So that's what you see. Wow, it looks way more. I think it might have been my hand. Let me see. All right, that looks better. So let me leave it there. So this is what you are looking at. Starting from the release point, right? Stop me when I'm going through the equilibrium position. So starting from the equilibrium release point, stop me when I'm going through the equilibrium. Yeah, here, right? So this is the equilibrium. And when you go below that, and this is the lowest point. And then you are back at equilibrium. And you are now at the highest point again. So let me zoom in. Can I just zoom into this? So this is the shape that you should have drawn. And in case you're looking at the other graph, let me hide it behind this one. Good. So how many of you drew something that looks exactly like this? And this is the sense in which I'm in, that it starts out with something that's close to zero slope. The slope increases up to a point here, and the slope actually starts to decrease. And then it gradually comes to a flat line here, and then the slope gradually increases again, and then decreases. How many of you drew that? Okay. Some of you, I saw you drawing something that looks more triangular, which is fine. So that's why we are going through this exercise. So intuition is kind of a recalling what you have seen before. And if you've never seen this before, then you need to see it at least once. So, all right, so that's the shape for a position graph. I thought there was one more question while we are here. Part C. What function might be chosen to describe this position x as a function of time? So if we had to, just to pick a function, any function, well, not any function, a function that fits this. If you had to pick a function to describe this as a, position as a function of time, what form of function would you pick? Cosine. Oh yeah, this would actually be cosine. So I might say this is equal to cosine of t. And we are going to have to fix this up a little bit. It has a general shape of cosine. Could you imagine this position function looking like a sine shape instead of cosine shape? Sort of depends on how I start it. So if you are looking at it as, so what if instead of starting it like this, if I started it by pulling it down, will it still look like cosine of t, or would you need to change it up a little? Abdi?
Yeah, it may look like sine.
So it's not sine, but negative cosine. Starts from negative position, goes up, and then comes back down. So to make it look like a sine, I have to do something that's more fancy, like this. I have to, give it a little initial velocity. So start it by going up. So what I'm trying to say here is that the difference between cosine and sine, it's a difference in the matter of where you start the motion. You could start it like from here. And if I say, okay, at my time equals 0 is when it goes past the equilibrium position, then that'll look like a sine actually. Good? Everyone okay with that? All right, so this is a good enough guess for now. I'm going to want to modify it a little bit later. And in case you're thinking about it, there are two things wrong with this particular form. Two things, and we'll come back to that later. All right. So the second intuition building exercise that I want to do is the next set of questions. So we looked at the position. All right, that seems fine enough. Now, what I want you to do is I want you to do the same exercise, this time for the velocity. So, position is a little bit easier because you can kind of look at it, see that it's moving up and down. So, velocity, it's a little bit harder. You have to think through it a little more. So, take a minute, check your answer with your neighbors. And I guess if you want to see the position curve, this was the position curve. And velocity curve will be different. All right, I think most of you have it. Some of you are fixing up what you had before. Let me just show you the graph. I mean, it was already down there. I hid it because I didn't want you looking at it. This is the velocity curve of the same motion that we did. So this is the position curve. This is the velocity curve. Is that as you would expect? Yes? So, hopefully you remember that velocity is the rate of change of position. So remember in calculus, that means comparing these graphs, this should, the value of at this point should agree with the slope at that point. So, here's one thing we can actually kind of check against something that we know already. What can you say about the velocity at the equilibrium position? So when the mass is at the equilibrium position, what can you say about how much, do you know anything, too open. Let's see. What kind of description could you give to the velocity at this same time as when the position is at equilibrium position? There's one particular thing you can say about velocity based on what we were doing a few weeks ago. Asia? Maximum speed from the consideration of conservation of energy. When you are at equilibrium position, your potential energy is at minimum, so that it'll make your kinetic energy at maximum. Now what we can do is we can actually look at the kinematics. So look at the slope at this point. This is, I guess in calculus you call this what? There was a name for this. I mean, the line is tangent, but this particular point, it was inflection point. Wait, inflection point, is that right? Yeah, inflection point. That's where your concavity is changing, right? This was concave down, and here it becomes concave up. Anyway, so this is the position where your speed slope is at a maximum. Because before this, it was at a gentler slope, and after this, it's at a gentler slope again. And when you look at the same point down here, well, yes, it is at the maximum absolute value of the speed, velocity. And the same thing happens as it's going through the same equilibrium going the other way. When you look at the velocity, or when you look at the speed, it's at a maximum again. Good? All of this makes intuitive sense? Yes. Okay, let's do one last thing. So it asks about acceleration. Oh, wait. Yeah, I don't know why I never really changed this. You know, I'm kind of running out of time, so let me actually skip this part E. You can do it on your own, and let me just show you this graph. So you saw position and velocity. What do you think it'll look like if I display the acceleration? Like, will acceleration look like a velocity? No, right? You're taking another derivative, so it shouldn't look like the function that you took derivative of. So what would the acceleration, would it look like anything on the board already, or will it look a little bit different from what's already on the board? Isha? Okay, different, how would you describe it? Like if you had to compare it to something else on the board. Flipped upside down. Yeah, let's try it. Let me display here. So this curve is acceleration. So it kind of looks like the position, except flipped around. And you can explain it based on the velocity curve. So this here, the velocity curve slope is downward, right? So your acceleration is negative. There's a point where your velocity curve is flat. Rate of your change of your velocity is 0. And that point happens to be the equilibrium position. So there the acceleration is 0, as I was claiming earlier. And then it goes through the cycle again. Good? So all of this motion makes sense? Yes? Yeah, I want to make this the motion that you can just observe by moving this up and down, that makes sense to start out with, because it's going to get a little bit math heavy. And I'll tell you a little bit of secret. So the secret to success in physics and really engineering is that for anything that you want to calculate, you should know the answer before you actually do the calculation. So if you're doing the calculation to try to find the answer, the thing is you're going to make a lot of mistakes and you're going to waste a lot of time. So people who are good at physics and engineering, they actually know the answer before they do the calculation. All the calculation does is it simply confirms what you already knew. So, so that's why I'm spending a fair amount of class time going through this exercise to make sure that you have a good intuitive mental image for the motion of this. So when we describe its position as a function of time, then that it looks like a cosine, like that's something that you know intuitively before you do any calculation. By the way, before we move on, let's fix this up. I said that there are two things wrong with this function. So did anyone figure out what was wrong with it while you're looking at it, thinking about it? No, not yet. Let me give you a hint. The thing that's wrong with it is units. So this is what I mean by units. So the quantity that's here, it has to have a very particular unit. This is an input to the cosine function. So it has to come in very particular unit. Right now it's coming in the unit of second. And I'm telling you, that's not right. I cannot put in 1 second into a cosine. I mean, what kind of quantities does cosine take as argument?
Pi,
Pi, what kind of quantities are those?
those are period.
Not period. Radian, some kind of angle, right? Now, what do you remember about radian as a unit? Asia? It's not a real unit. Radian is just a reminder. So actually cosine takes a unitless quantities. And this is actually true of any special function. Exponential takes a unitless quantity. Logarithm is supposed to take a unitless quantity, although sometimes you can cheat. Any kind of special function that you remember learning in your math class, they are supposed to take only unitless numbers. So only polynomials can take a unit. So this is supposed to be unitless. And what you see here is clearly not unitless, right? Right? So we are going to have to introduce a coefficient here to fix that. We are going to end up putting up a coefficient here that's going to have correct units to make this unitless. What is unit of this coefficient? 1 over second, right? All right, so let's say this is, when we figure out the, whatever this is, it's going to have unit of 1 over second. So that was the first thing that was wrong about this function. What's the second thing that's wrong about it? Second thing that needs to be fixed. Tickle? Any ideas what's wrong with this form here? We said the position looked like a cosine, which wasn't too far off because, you know, that looks like cosine, right? But, so we studied a cosine of t, but that doesn't have a correct unit. So we had to fix that. I'm still saying this is still wrong. It's not exactly correct. This has to have a correct unit. The left-hand side has unit of meter. So this also has to have a unit of meter. The result of cosine, does that have any unit? No, it's just a ratio, right? So it has no unit, which means you need another coefficient to make sure that you get the correct unit that will agree with the left-hand side. And this is going to have unit of meter. Yep. So once we have that, we can actually write down the second thing that I kind of didn't want to do before I write this down. So velocity, we described as time derivative position. We can actually do this derivative. Velocity as a function of time is equal to the derivative of this position. So, well, A is constant. What's the derivative of cosine? Negative sign. And I have to use chain rule. I took the derivative of the outside, and then I have to take the derivative of the inside. When I do that, I get B out. So when you do the derivative, you get minus A times B sine of BT. Right? This minus sign that agrees with what many of you are drawing before. So let's just double check the unit of A times B. A times B has unit of meters times 1 over second or meters per second. Is that what you would expect? Yeah, unit of velocity. Yeah, and if you do one more derivative for the acceleration, you'll get that. Good. All right, so that's all for the intuition building portion. Hi, in this video, I will illustrate some interesting, unexpected, and general features of simple harmonic oscillators. We are going to use this PHYS simulation, masses and springs, but I want to emphasize that the range of phenomena that can be described as a simple harmonic oscillator motions are very broad. It goes beyond just masses on a spring. All right, so this is masses on springs. When you hang masses on them, you see an illustration of Hooke's law. Where the masses come to a stop are equilibrium positions. This is where the net force on the mass is 0. The downward force of gravity is exactly balanced out by upward force of spring. In all situations that exhibit simple harmonic oscillator motion, there is going to be a stable equilibrium position. When you push your system away from the stable equilibrium, there is a restoring force which brings the system back to the equilibrium, but not immediately. It oscillates back and forth a few times. In fact, the whole reason it comes to a stop at all is because of friction. So let me get rid of that. Now, when you set the mass in motion, let me mark the equilibrium position. It'll oscillate back and forth forever. You could look at this as an illustration of conservation of energy. Over many cycles of oscillation, the total energy remains the same. The only thing that happens is that the energy sloshes back and forth between kinetic energy and the total potential energy. Alright, so far nothing too surprising. Now let me set up a situation here. First, stop the time while I'm setting it up. Let me remove this 50 gram mass, hang the 100 gram mass, and this is the equilibrium position. So I'm going to set them at different amplitudes. Small amplitude, large amplitude. Now, before I unpause time, here's the question. How do you think these two oscillations will be synchronized? Will one oscillate more quickly, higher frequency, higher hertz than the other? Which one? Let's see. What you are seeing here is that these two simple harmonic oscillators with different amplitudes oscillate at the same frequency. This is a general feature you will see with anything that is approximated as a simple harmonic oscillator motion. You can try to intuitively see why this might be the case. The oscillator with larger amplitude has a larger distance to travel, but because of its larger amplitude, it also has greater energy, which means larger kinetic energy and larger average speed. What I want to emphasize here is that this is a very general phenomenon. This amplitude-independent frequency of oscillation is so general, it is given a special name, natural frequency. That is the frequency at which a given simple harmonic oscillator would oscillate, given a little initial kick from equilibrium. As you see here, it doesn't matter how much of an initial kick you get. In order to change this frequency, you have to change the system itself. For example, if you change the mass, then the frequency will change. The lighter mass means that the oscillation can happen faster. Given the same kinetic energy, the velocity is higher if mass is smaller. Another way to change the frequency is by changing the property of spring. If you use a more stiff spring, the natural frequency shifts to a higher frequency. While it's paused, let me hang a 100 gram mass here and unpause the time, and let's see. In other systems of simple harmonic oscillator, what their version of spring constant and mass is will be different. But one thing you can take away is, if you have a simple harmonic oscillator, then its natural frequency is a property of the system. You have to change the system itself, not just the amplitude. By the way, this is how one can measure a mass in the weightless environment of space. You set it to oscillate on a spring, and by measuring its oscillation frequency, you can figure out what its mass is, because the natural frequency, spring constant, and the mass are related to each other. Alright, so this was a short demonstration of a simple harmonic oscillator motion. Please let me know if there are any questions. The concepts we introduce here will be useful for other simple harmonic oscillator setups and for the discussion of waves. Bye. So, you can still run it with that workaround, but HTML5 is better. So let me just use the HTML5 version to show you what you can also see with the Flash version. So HTML5 version is better, mainly in that it runs on any device. So the Flash versions won't run on mobile devices. This simulation will run on tablets, on phones, on practically any modern device. So this is a spring simulator. I guess that energy graph is a little bit in the way. Oh wait, I need to. So this is one of the nice thing about simulation. I can. So right now, this oscillation that I set off at the beginning, it kind of gets smaller towards the end because of what's simulated in as a damping. That's simulating real world processes like friction and air resistance that tends to convert this mechanical energy into thermal energy. um, when I'm trying to describe an ideal system, that kind of gets in the way. So I got rid of damping. So if I were to show energy graph again, this will go on forever. So I have that. And let's see here. Can I? Yeah, I can control the simulation speed. That's good because sometimes I'll want to talk for a while. Um, so okay. So let me quickly overview the idea of natural oscillation frequency, which so okay, that's a good place. So this line is the mass equilibrium. Having this line is useful for illustrating the amplitude of oscillation, as in the maximum displacement from this equilibrium position. Uh, so if I start off the mass from here, let me put a movable line here. The distance separation from here to here would be the amplitude. And as this oscillates, it's going to go about the same amount of distance above the equilibrium and then below. So if I let the simulation run, that's what that looks like. And I can do period trace to show what one period looks like in this setup. So the idea of natural frequency of oscillation comes from this rather interesting, which could be experimental observation. If I measure this period, you will see that the period, which is related to the frequency and the angular frequency in ways that you will see in the chapter, um, it remains constant under quite a bit of different circumstances. So I'm going to run this stopwatch at the next cycle. So, and as I measure a single period, sorry, that was a bit, let me catch it on its downward cycle so that it matches the graph that you will. Is it? Okay, I think it's switching each time around. Okay, I'm gonna catch it here. Okay, and I'll measure it for one period. So here the period is about 0.82 seconds. Okay, and when I change some parameters of the oscillation here, for example, make the amplitude larger, larger by let's say factor of 3. So this is about twice the distance, 3 times distance. The amplitude of oscillation is now going to be 3 times what it was before. So when I run the simulation, and let me, okay, so I'm gonna let that go and I'll catch it the next time. Okay, reset and then catch it here. even though it's traveling 3 times the distance, you see that the period remains the same. And this relates to what we call natural frequency of oscillation. When you have a spring mass system, it has a frequency at which it naturally oscillates. Now, it can be changed, but in order to change it, you have to change the properties of the system itself. For example, you could change the mass. Instead of hanging a 100-gram mass, you could hang this larger mass. Then its period would be, it should be smaller. So if I let it run, let me just start the simulation here. And so, okay, let me catch it on the next time. Oops, sorry, I missed it. Okay, I'm gonna catch it on, is it always on the way up? Okay, so I'll catch it on the way up. Yeah, the period is longer, meaning it's a slower oscillation. Oh, it looks faster because I'm on normal. Let me do it again on slow so that it kind of matches up. Or yeah, let me just spend this time. Um, so it goes down, and then on its way up, I'll catch it. Okay, on its way up. It's moving at about half the speed that it was moving before. So um, yeah, and this can actually be used to measure the mass. That's one of the ways you can figure out this mystery mass. So yeah. So you can change the period by changing the mass. That's one. And you can also change the period by not changing the mass, but by changing the changing the property of the spring. So just to double check, this one should have about 0.8 second period. Let's just double check to be sure. I think I clicked it a little too fast. So this was the system we started out with before. Now, if I make the spring stiffer, for example, make it have a larger spring constant, then it oscillates faster. So its a period will be smaller. So let me pull it down here, and when I let it go, I'll just let it go for one cycle and then catch it on the next time it's on the way down. You see that period is smaller. Now, but given the same, let me just reset everything. Given the same properties of the mass, of the spring, then this natural oscillation frequency, it's a constant. It's a characteristic feature of what we call simple harmonic oscillators. And there's a reason we cover this idea of simple harmonic oscillator or harmonic oscillator. It's because so if you're just thinking of how often am I going to see a mass on a spring, then yeah, you're not going to see that often. But the reason this is useful is that there are just so many systems in the real world that can be approximated just like this mass on a spring like a system. One example of that is actually pendulum. So there's nothing like a spring here. It's just it's pendulum. It's a mass hanging at the end of a string or a rod. And when you take a look at it, you will see that it exhibits properties similar to a simple harmonic oscillator. Let me use this period timer to measure period again. So at this very small oscillation, when I measure the period, you see that the period is 1.7 second or so. And if I change this oscillation amplitude so that it's oscillating at a larger amplitude, you'll find that the period is about 1.7, so about the same. Now, if you're watching this carefully, you will notice that it's changed a little bit So at this angle here, it's 1.68 second. And when I move this to a smaller size, so about 2 degrees, it's not 1.68 second anymore. It's quite close to 1.68 second, but it's not quite 1.68 second. Now, if I were measuring this by hand, I would have said, oh, it's just my reaction time. I can't get it exactly right every single time. But this is a period clock. It's built into the simulation. It always gets the exact same time. So, so this illustrates the way in which many systems in the real world behave like a simple harmonic oscillator in this way. You can approximate them as a simple harmonic oscillator. So many real world systems are not exactly like a mass on a spring. That's kind of an idealized system. It has certain properties that one always hold. But when you take a real world system, put it under certain conditions, then very closely it follows the properties of simple harmonic oscillator. So this is one example. When pendulum is oscillating at small angles, the period or the natural oscillation frequency is approximately constant at a value. So right now this is at 2 degrees, and at 2 degrees, the period we measured was 1.6785 seconds. Um, yeah, let me write that down somewhere because I'm gonna start to forget it if I try to remember it. So let me just to build a table so that you can kind of see how it changes. At 2 degrees, I have a period. So this is the gonna be the angle, amplitude, and this is gonna be the period time. I have 1.6785 seconds at 2 degrees. Let me try doubling the amplitude. So instead of 2, let's have it at 4 degrees. And when I measure the period, it's close to this value, but not quite. At 4 degrees, it's 1.6789 seconds. And let me just double each time. I think then it's not going to take too many tries to actually cover the whole range. Let me set this at 8 degrees and measure the period again. And it's still quite close. And this is what I mean. This is approximately simple harmonic oscillator. So between 2 to 8 degrees, the amplitude changed by a factor of 4, but the period barely budged a little bit by like a 1.5 millisecond, or about 2 milliseconds, I guess. It's practically unmeasurable, except that I have a very good simulation. Let me try setting this at 16 degrees. Keep doubling the amplitude. So at 16 degrees, it's okay. Now if I round it, it'll be 1.69 seconds instead of 1.68. So it's beginning to change here. And it's beginning to change in a more measurable way. And this is where you see approximation starting to break down. This is at these larger angles is where you will see the period does depend on the the amplitude of oscillation. And we call this N harmonicity. Sorry, this is getting to be a little annoying. Let me just write that down. It's becoming from a harmonic oscillator, it's becoming an a harmonic or n harmonic oscillator. So at 32 degrees, period is 1.7117 seconds, and by this point I can start to measure it by hand if I take more than a single period. So let me move this to now 64 degrees and see what that looks like. I think that's where I'll end it. So let me measure the period here. Now, this pendulum is moving faster, especially at the bottom, but because it's moving such a longer distance, it takes a longer period. And in the case of the mass on a spring, simple harmonic oscillator, this those two balanced out how fast it moves and the longer distance it has to travel. It balanced out to keep the period the same. But with this real world object, like a pendulum, it doesn't quite, it starts to not exactly balance out, so that the period does eventually start to change. And but it takes quite a large amplitude of oscillation before you see that in a noticeable way. So, and you will see this kind of an example of a simple harmonic oscillator in many different situations. Basically, anytime you approximate motion of something around the stable equilibrium, if you look at small enough amount of motion, it'll look like a simple harmonic oscillator, um, because it, yeah. So that's really why we spend so much time on mass on a spring, which is kind of unrealistic. It's not something that you would see that often, because this becomes a model for real world things that so maybe you will never have to deal with the pendulum, but if you are dealing with like chemistry, molecular bonds, the vibration of those molecular bonds can also be approximated as kind of a simple harmonic oscillator. So yeah, this is the demonstration of a pendulum as a kind of an approximate simple harmonic oscillator. So this is the demo I was talking about last time. So last Tuesday we looked at oscillations, and you looked at simple harmonic oscillation with a spring, with mass on this spring, right? That's the demo that we have used for a while. So we introduced the oscillation with that because that's what you're familiar with. It's easier. But I want to use this setup to illustrate one thing and actually talk about one more thing in a little more detail. So this is an example of pendulum. You have actually seen pendulum before, right? And you see that this moves back and forth like in a, like tick-tock kind of regular way. The same way this mass was oscillating on the spring in a regular way. So you can imagine applying the mathematical description that we were applying to mass on a spring the exact same way to here. So this is another example of simple harmonic oscillator. If we had to give it a name, it would be pendulum. And we'll go through the derivation of this pendulum equation of motion so that we can see that the solution to this looks exactly like what we looked at on Tuesday. What this setup is for right now is to illustrate what's called coupled oscillators. So that's this demo that you saw before, right? Where it started out oscillating up and down, and then over time it's rotating that way. I prefer this demo because this is, one, easier to explain, and two, easier to manipulate. So let me demonstrate one of the features of this coupled oscillator with this demo. So this is how I'm going to set off this oscillation. I'm going to set it off so that only, let me give them a name, Alice and Bob, A and B. So I'm going to start this motion with only Alice moving. So I'm going to pull Alice back and let go. And as you watch this over a period of time, I want you to notice what happens. So Bob starts to move, and you will see that over time, Alice actually comes to a stop. There's a moment when she comes to a complete stop. Well, when it comes to, it's a mess. I know it's right here. Alice is at a complete stop. But it doesn't stay there. It actually gets moving again. And then over time, Bob will come to a complete stop. Wow. I'll wait until Bob comes to a stop and then I'll continue. This does take a while because, yeah. So this is, wait, it hasn't come to a stop yet. I mean, you believe it'll come to a stop, right? Okay. So this is an example of coupled oscillator. And I will tell you right now that coupled oscillator as a topic, it's an upper division level topic. So other than doing this demo and giving you some terms to I don't know, Google search. We won't really talk about it. But it's an upper division level topic to actually deal with it in detail. But we can handle it in a conceptual level. In a conceptual level, this is one way I can describe it. So I start by putting energy into A. And as A moves back and forth, what you are saying is that some of this energy transfers over to B. And then you wait long enough, that energy transfers back to A, back to B, back to A, and so on. If there was no friction, this would go on indefinitely. And so what do you think is the mechanism of energy transfer? Tikal? Yeah, so when I put energy into A, how is that energy that I'm putting into A getting transferred into energy of B? Yeah. Yeah. As you watch this, you realize that, notice that this support is moving back and forth, right? Yeah, you might have thought that's because I don't have proper budget to put a good support. But actually, the fact that the support moves, it's an important part of how this works. I haven't actually tried this, but let me try this. Let me actively stabilize it just by holding on to it. Can I do it? I don't think I can actually do it. So there's a reason this is a 2 kilogram mass. It's heavy enough so that it can actually shake the support. Now, let me show you a little bit of change from this. So they look the same length, all symmetric. I'm going to just change the setup here slightly by wrapping the string around this mass. I'm going to, by wrapping the string around this mass. And I'm trying to avoid it having like unwrapping and just tumbling down. Let's see. I don't know, it's a pretty heavy mass, and this paper clip is really flimsy. All right, I think that'll work. All right. So, all right. So let's try it again. I'm going to put energy into A. Let's see if that transfers over to B. So some of it does, right? But not quite. In fact, we can wait for 10 minutes, and not enough energy will really go into B. And since it's not going into B, it stays in A. So what do you think was the biggest difference between the setup we had before and the setup now? So this support, it's still shaking as this moves back and forth. So why is that energy not being transferred into this? Wait, what? So the length is different, but it has really nothing to do with the radius, nothing to do with the torque. Yeah. Asia, you're going to say something? Yeah, so the difference in height is different, but you know, the height is different. But I want to express it in a way that it's not specific to this pendulum setup, because the description that we are trying to give, it's something general that applies to all simple harmonic oscillators, whether it's based on pendulum motion, whether it's based on spring motion. Whether it's based on spring motion, this feature that we are going to describe will apply to all simple harmonic oscillators. So, let me show you. It's kind of hard to guess at this without having seen it. So you see how fast this is moving back and forth, right? Now watch. I'm gonna make this move by putting energy into B instead. Do you see a difference? What's different? Ali?
Energy didn't transfer to Alice.
Yeah, so it's not transferring. We know that already. But what is different in how A is moving and how B is moving?
Faster?
Yeah, this is faster. So this is one of the features of the simple harmonic oscillator that we looked at last time, and we didn't really spend enough time on it. That's why I wanted to highlight it. So when you look at simple harmonic oscillator motion, there's really if you had to pick out the one thing that characterizes a simple harmonic oscillator motion, is that it has a natural frequency of oscillation. A simple harmonic oscillator motion has a natural frequency of oscillation. And you saw this with the mass on a spring system, right? We derived, so if when you describe the motion of the mass this way with this function, the height of the mass as a function of time is equal to some amplitude times cosine of omega t plus the phase factor. What you saw last time was that a lot of these parameters were variables or undetermined, except one. The angular frequency here was determined by the equation of motion. So for mass on spring, you saw that this omega was equal to square root of k over m, right? And this is the property of the system. It's a constant value. So if you have some mass that's hanging from a spring, then it naturally will oscillate at this particular frequency. And no amount of what I do, like if I try to make it oscillate, oops, too much. If I try to make it oscillate at a greater amplitude, that will not make it move at any faster frequency. I mean, it'll move at a faster speed, but the frequency will be the same. That's what you saw in the lab, right? So that feature transfers over to any other system that you would describe as a simple harmonic oscillator. So that's what you are seeing here. These two different pendulums, they have different parameters, different length. And that length somehow must go into the equation that determines its natural frequency of oscillation. And we'll take 20 minutes or so to look at that. So that's what you are seeing here. These two have different natural frequency of oscillation. So in terms of trying to transfer energy from A to B, as this moves, it shakes the support at a particular frequency. And the frequency that this is shaking the support at, it's mismatched with the frequency that this needs to gain a lot of, because you can actually imagine making this move with a very tiny amount of force. I think, can I do it with my breath? I might be able to. So I'm out of breath. If you do the correct frequency, you can do it with a very small amount of force. This is tied to something called resonance that we won't spend a lot of time, but that's the important part in how energy transfers from this to this. So the shaking of the support, it's very small. It doesn't cause anything to shake at a great amplitude, but when these two have the same length, so from the equations that we are going to go through in a little bit, these two happen to be oscillating at the same frequency. So that when I get one to move first, then this shakes the support, and it's shaking at just the right frequency that with each cycle, it's putting more energy, more and more energy into B. And I guess as it's doing that, so it's losing energy, so it slows down, comes to an eventual stop, and then at that moment this is shake. Wait a little bit. So at this moment, B is shaking the support, and the shaking of the support puts some of the energy back into the A. Good. So let me just finish this discussion with a coupled oscillator. So in upper division, they describe this in terms of normal modes. And one way you can actually describe it is this system as a whole has two different ways it can shake. That's the normal mode. So let me write down because for coupled oscillators, normal mode is the mode in which there's one single frequency of oscillation and it's sort of not fixed. We call it stationary state sometimes. If you watch it, you will see it. So it has two normal modes. It's one normal mode is this one, where these two shake at the same, like in sync. Then it's, you will see, if you watch it for a while, you will see, oops. I did not think that through. So this is the system fixed up. It's shorter than it was before. I think it still works. So let me just demonstrate that it still works. If you start the motion, then it does do that. Now, what I want to, I'll wait until this stops so that you can see that it comes to a complete stop. And then as this continues to move, this now moves back and forth again. Good? So you're convinced that it still works. So this is the normal mode that I was trying to describe, but I could only gesture before. So this is the one normal mode that moves at a particular frequency. And you see, look at the motion of the support, how the support moves along with both the masses moving together. And this is the other normal mode. This has two normal modes. What you just saw was one, and this is the other normal mode. And look at how the support actually doesn't move as much because it's getting pulled and pushed the other way. So as a result of that, these two normal modes, these two stationary states, they have different frequency of oscillation. So what you are seeing here as this motion, you can describe it as sort of combination of those two normal modes happening at the same time somehow. And so when these two normal modes, this and this, when they're completely, when I sort of synchronize, imagine one starting this way and the other one this way. At time equals 0, it will look like this motion. And as this shakes back and forth, I guess normal mode that's going this way, it has a faster frequency. So that sort of starts going faster. Then at some point, it'll come to a combination that looks like this plus this. So that's when this is at rest and this is moving. And so all of this will make a little more sense once we've done something called the wave interference in the context of waves.